Hello and welcome. This is Piotr Przybicin. In this video I will present the changes made to the energy consumption calculator. I click here on the button to launch the calculator. This is how the calculator window currently appears to us. We have introduced here, or rather completely redesigned, the user interface, which is now much more user-friendly, because visually we can choose or configure the ventilation system that we will be calculated. Before we get to that, first we will enter initial here data, and here to carry out the calculations we need to choose the country for which we are performing the calculations. We can choose one of 223 countries worldwide here. I will perform the calculations for Poland. But here we choose the city for which we will perform these calculations. I'm choosing Warsaw, while we have the option to choose from 5,300 cities worldwide. Next we select here the CAV system, which is a constant air volume ventilation system, or a system with variable ventilation air volume. For the purposes of our example, let's assume it will be a constant air volume ventilation system. We declare the atmospheric pressure, or the altitude above sea level. If we enter a value here, then the pressure will automatically be recalculated, and vice versa. In this field we enter the time range for which we want to perform our calculations. We will conduct them for the entire year, therefore I leave these fields unchanged. Here we enter information and data regarding our heat source for the individual sections of the ventilation unit or the ventilation system that we will be calculating. And so here we have to enter the seasonal efficiency of our heat source for powering the heater of the ventilation unit. We mean this heater here. These indices here, which represent these efficiencies, are adequate for their respective sections. In connection with the above, well, we assume for the purpose of our example that we will have a heat source in the form of a heat pump with the seasonal efficiency of heat energy production of 350%, that is 3.5. Here we choose, of course, what it will be powered by. Whether it will be our electrical energy network, or perhaps some other form of energy such as photovoltaics, wind energy, or another. Depending on what we choose here and the country we choose, we will be informed some carbon dioxide emission indicator per kilowatt hour. This data comes from the service Our World in Data. Meanwhile, the climate data related to this field comes from the Weather API portal. We fill in all these fields here concerning the heater. Here we have the cooler. Here we have the source efficiency for the steam humidifier. Here we have the seasonal efficiency for fans. Here it's also important to note that this is not 100%, because we have even just inverters, which have losses, energy losses, when converting electricity here. Here we have the seasonal efficiency for the antifreeze heater. This antifreeze heater is located here. We generally use it in conjunction with cross-flow, counter-flow, or glycol heat exchanger. Because in cold climates, these types of exchanges tend to freeze, and they simply need to be protected. Generally, if we use a rotary exchanger, in this case the frost protection heater is unnecessary. Okay, so and one more thing, here we introduce the efficiency of our secondary heater for air drying, which is used in the process of drying air. Here we have a window with our results, which will present the useful energy, that is the seasonal energy demand, the final energy. In other words, the value of useful energy, that is seasonal energy demand divided by the efficiency of our heat, cooling source, and so on. Here we will have the cost of our energy, for which the investor will physically pay. and the carbon dioxide emissions that the given section will generate. This data pertains here to the heater, the cooler, the humidifier, and the fans. Here we have an adiabatic cooler, okay? Here we have the value of the amount of water condensed during the drying process, the amount in tons of oil equivalent, which is calculated based on carbon dioxide emissions, which is an extremely important parameter when trying to obtain funding for the so-called white certificates in Poland. It doesn't necessarily have to be important in other countries, but from the point of view of Poland and currently possible grants, this is a very important indicator. And here we will have presented the total operating cost of our ventilation unit, which is in fact what most interests the investor. Here we will have the graph of our energy consumption. Depending on the elements we want to have presented on this chart, we will observe them here. Will they be useful energies or final energies? That depends on the user. Here we will see pie charts showing the structure of energy consumption, emissions, carbon dioxide emission structure, cost structure, and so on. Here, to perform the calculations, we still need to choose the operation scheme of our ventilation unit or ventilation system. Let's assume that for this example we will simply operate 24/7. Okay. And now we can move on to our ventilation system selection interface. As you can see, we can compose a system here, which will consist of a heat recovery exchanger, a mixing chamber, a supply fan, an exhaust fan, a heater, here preheating air during the winter period, an air cooler, a secondary heater needed during dehumidification, steam or adiabatic, depending on the choice of options. Here we have steam, and here we have adiabatic. And possibly we can also consider direct adiabatic cooling on when supplying air to the room. However, it is important to remember one dependency here, that if we use adiabatic cooling, whether we choose a mixing chamber or not, the cooler will be calculated as if the mixing chamber did not exist. Because we introduce huge amounts of water during the summer when humidifying, we do not take this into account. With the mixing chamber, we just assume by default that we are working 100% on fresh air. Okay, I will briefly explain all the fields that we have presented here. So starting with the antifreeze heater, here we only really need to input the energy carrier price for the antifreeze heater. Next we have the heat recovery exchanger, and it can be different types. It could be a cross-flow or otherwise called counterflow exchanger, depending somewhat on the design. So here we can enter the efficiency separately for summer and for winter. If the manufacturer were to declare different values for these parameters, we can choose a rotary one. Then we also get the option to input moisture recovery efficiency if we are dealing with a hygroscopic rotary exchanger, and we have the option to choose a glycol diffuser. In this case, the value concerning the moisture recovery efficiency becomes inactive again. Next we have the mixing chamber, where we can declare the degree of air recirculation. Supply fan, where we declare the supply airstream into the room. Total pressure, which takes into account the resistance of all sections of the ventilation unit or ventilation system, including ventilation ducts, that is hydraulic resistance, pressure drops on ventilation fittings, and so on. Here we have efficiency here of the fan, and the energy carrier price for the fan for electricity is 1 zloty. As you can see here, I assumed everywhere. For this example, we will have electrical energy, meaning a heat pump, a chiller, and all other components are simply powered by electrical energy. We have the same for the exhaust fan here. We introduce the exhaust airstream as well as the total resistance of the exhaust section, considering the ventilation ducts. And the efficiency of the exhaust fan Here we have an air heater, and here we set the temperature. For the supply air in the winter period, we introduce the starting or end temperature of the heating season when we heat the cost of the medium. Here, additionally, we have the option to include such a feature as consideration. If we use a mixing chamber, we can oh no, sorry, not in this case. In other words, we also indicate here whether we take into account the energy gain from the supply fan, meaning when the supply fan is operating, it's obvious, it causes air heating. Să găsiți că taki pasitek of the ventilation system, which simply physically relieves the heaters of the ventilation unit. So we can just highlight and account for it here. Additionally, if we perform calculations for fully air-based systems that air condition or heat our rooms, in this case we can include that the temperature of the supply air is not constant but variable depending on the outside temperature. And here in this case we can declare a heating curve. In other words, we perform calculations for the room's heat demand under design conditions. For example, for Poland in the third climate zone, the extremely low temperature is -20 degrees. So for this temperature, we perform calculations of the heat demand in external software, unfortunately, and enter this value here. If it is, well, I don't know, 20, let's say 15 kilowatts, then I enter 15. The program will automatically determine here the target supply temperature that must be achieved at -20 degrees to meet that 15 kilowatt demand heat, and automatically determines the heating curve in the form of a straight line. The user can modify these values here themselves. Here, for the end of the heating season temperature, we declare what the heat demand is. In this case, it is 0, and the temperature, in this case, of the air supplied to the room. It is isothermal 20 degrees Celsius. Okay, we accept. We move on to the air cooler. Here, similarly, when determining the power of the cooler, we can take into account the heating of the air in the fan. So we check this function. Here we have the supply air temperature in the summer period, and this can be a constant temperature to which we will cool, or variable according to the cooling curve, similar to the heating curve, meaning in external software. We perform calculations of heat load for some extreme temperature. I'll mark it now. And here we might have a situation where we are doing calculations, and we find that with an external temperature of 32 degrees plus, for example for Poland, for the Polish territory or another country, that's up to us. As I said, the program calculates all these values for 5,300 cities from around the world. Let's say we also have 15 kilowatts of heat gains, and the program automatically calculates that with a temperature of 32 degrees and 15 kilowatts of sensible heat gain. In this situation, the supply air temperature will need to be plus 15 degrees Celsius after the cooler. Here we input the initial cooling temperature, let's say it is 15 degrees, and at 15 degrees outside we have 0 cooling demand, and in this case the supply air temperature is isothermal. For summer we declared there plus 24, so it automatically suggests that here as well. And we have here is the designated cooling curve in the form of a straight line in this case, but of course we can freely modify it, or so we can, for example, declare that we want it to look more like this, and the program will take that into account in the calculations. Here additionally we can also introduce functions for the mixing chamber, just like for the supply fan, also factoring in this exhaust fan in the calculations. So in this case the program will, depending on the position of the fan, because if in the actual ventilation unit this fan was located behind the mixing chamber, then it should not be marked. But if the situation is analogous to this one, where the fan is in front of the mixing chamber, and the mixing chamber will have a certain degree of recirculation, Then if we turn on this circuit, then the program will also consider both the heater and the cooler in the selection. The amount of energy that will flow with the recirculated air to this place will be subtracted from the heater and added to the cooler to a degree equal to the degree of recirculation, of course. Alright, next we have the secondary heater for dehumidification. So in fact, if we want to perform dehumidification, we simply need to select this option here. Here we also have two options to choose from. Either we choose to dehumidify to a certain degree, regardless of the moisture content in the supply air, or we choose that this heater operates in a way such that we simply heat the air after cooling to a certain specified temperature here of the secondary inflow. However, I think the option where we declare the absolute moisture content to which we want to dry the air is definitely more useful. This is non-condensing equipment, I'll add. Okay. Here, if we input an absolute humidity level that cannot be achieved at a certain cooler wall temperature, we will receive an appropriate message about it to lower the surface temperature of the cooler. In other words, lower the coolant parameters so that dehumidification to a given level of absolute moisture content is possible. Next we have a humidifier, and here we have a few options. It's either a STEM humidifier or an adiabatic humidifier, and additionally we can choose whether we will humidify according to around relative to the sensors placed after the humidifier, or according to the sensor located in the room, because we might have two different values here. If we choose for our humidifier to operate according to the sensor in the supply air duct, then its operation will depend on the set value of relative humidity we want to achieve and the supply air temperature in the winter period. However, if we select according to the sensors placed in the room, we will then effectively control the operation of the humidifier depending on the set parameter in the room. Okay, but for now I choose that we will, according to the sensor placed in the ventilation duct, which means we humidify to a relative humidity of 40%. And here we can also change it to 40 for the sake of this example. Here we have the option to include the adiabatic cooler, but for the sake of this example, I will not consider it at all for now. Okay, so we have entered our data in this way. Let's perform some calculations, but let's start with a simple ventilation system. I mean that initially we won't have any heat recovery or heating or mixing chamber, nor will we have, let's assume, dehumidification. We only have a heater, cooler, humidifier and exhaust fan. Because we have a separate exhaust fan here, we have no heat recovery. Consequently, the hydraulic resistance of this line will be very low. I assume for now that it is 100 pascals. Here we have a similar situation. We will have an air filter here, but let the resistance be 800 pascals in this case, which will allow us to overcome the hydraulic resistance, ventilation ducts, heater, cooler and humidifier, and of course a filter which is here somewhere. It is not crucial from the program's point of view, so we just declare it rigidly as the sum of all these resistances. Alright, so with all these data already entered, let's conduct some calculations. And in a very quick way, as you can see, the program carried out a simulation of such energy consumption. And what do we see here? We see that our ventilation system configured this way for the city of Warsaw will cost almost 147,000 zlotys per year. 147,000 zlotys annually, which is really a very high value and is of most interest to the investor. And such a ventilation system will emit nearly 50 tons of carbon dioxide. throughout the operation of this ventilation system, 4,365 liters of water will be condensed. In this way, we see how the energy consumption structure is presented. We see that the most energy consuming element of the whole system is the humidifier, the steam humidifier in this case, because we have chosen steam here. After performing such calculations, we can export or save it, but let's say export to an Excel report, which I will quickly show now. Okay, it is being created for us here. This is how the report is presented. Generally, we have all the basic input data we entered and the heating curve, the cooling curve, the weekly schedule of the ventilation unit or ventilation system operation, the results here of the usable energy, final energy, and carbon dioxide emissions. Pie charts presenting it graphically. Then a window showing the diagram of our ventilation system that we were implementing and the annual courses. And then we have breakdown into individual sections of such a ventilation system. So here we have detailed graphs showing the seasonal energy, demand energy, meaning usable energy for heaters, final energy for heaters and annual carbon dioxide emissions. Similarly for the cooler, similarly for the humidifier, in this case steam, and for the supply and exhaust fans and the total carbon dioxide emissions in this case. And at the very end, a legend that helps us understand all the terms used in the program. Okay, I am closing it. And okay, and now having a ventilation system selected in this way, we can ask ourselves the question of how it can be optimized. Because, well, the investor and physically they will pay nearly 150,000 zlotys for the operation of such a ventilation system. So we can easily optimize it to work much more efficiently. And thanks to this, we can also calculate a simple return on investment period to achieve certain savings effects. Therefore, at this moment, I am adding a heat recovery section to our calculations. Let it be, first of all, an exchanger, counter-current exchanger. In this case, I am also introducing an anti-freeze heater, because in Polish conditions, where we have a cold climate, the counter-current exchanger will freeze. So I select this option. Additionally, since we have introduced a heat exchanger, in this case, I must automatically increase the required pressure of such a fan, because it has to overcome the hydraulic resistance of the additional exchanger, as well as an air filter, which will have to be introduced, meaning effectively, without checking the manufacturer's technical data, I can assume that this increase will be a minimum of 350 pascals. So in this case, we will have a value of 450 pascals here. However, in this field, the filter had to be assumed already. So I only add the hydraulic resistance of such an exchanger. Sorry, in this case, it will be 1000 pascals. And in this way, we obtain a new configuration of the central unit, taking into account the heat recovery exchanger. Okay, so let's see. We have 147,050 tons of CO2 load. We include so the introduction of such an element into the ventilation unit or the ventilation system. We achieved savings. We still have nearly 40,000 zlotys left, and we say, well, 12, let's say, tons of carbon dioxide. But that's not all, of course, because now we're looking at our pie charts, and what can we observe? That the biggest energy consumer is the humidifier, which we can also optimize. And the only thing we should essentially do first is, for example, the introduction of a rotor, a rotary exchanger, a hygroscopic rotor. In this case, our antifreeze heater is no longer needed. So I introduce, disregarding the manufacturer's technical specifications, efficiency of 70% here on the hygroscopic bed. The hydraulic resistances for such an exchanger, I assume, are very similar, and I perform calculations. And what do we have here now? The price or operating cost has dropped by another significant amount of money. because it was 113, meaning we saved another 30,000 zlotys. So from our initial cost of 150,000, it has now become 84, and from 50 tons of CO2 it has become 28. Of course, we can still consider whether to introduce, for example, a mixing chamber, if we have such an option, meaning in the room for example, we have an excess of fresh air compared to the amount of air needed to assimilate heat gains and cover heat losses. Can we introduce a mixing chamber? If so, it is worth introducing it. And in this case, depending on the number of people present and hygiene needs, we can introduce some degree of recirculation. I assume that for the purposes of our example, it will be 50% here. In connection with the above, we take 5,000 from the room, it flows through the mixing chamber. Here, 2,500 is recirculated in the chamber. Here we draw 2,500 from the intake. This mixes here, and 5,000 cubic meters flows into the room, and we expel 2,500 cubic meters of air out an hour. I would like to point out that these values are slightly different due to differences in densities that occur with flows in the various sections. However, we didn't want to complicate it in any way, therefore we left these values as simple algebraic subtraction. In practice, all these flows are considered as mass flows, because in every ventilation unit we deal with changes in the volumetric flow of ventilation air due to changes in the humid air density. However, for clarity, most designers operate with streams, volumetric streams. In connection with the above, we went for perhaps, let's say, a slight simplification. Nevertheless, the program calculates according to a constant mass flow, but presents volume flows here. Okay, so 50%, we perform calculations, we observe how this compares to our values here, and we manage to reduce our operating costs a little bit more. So now we can really say that we have reduced the operational costs related to the ventilation unit by half. Of course, we can still check what would happen if we used an adiabatic humidifier instead of a steam humidifier. So we choose adiabatic and we perform calculations. Here I would like to draw attention to one thing. If we choose the adiabatic humidifier, in this case the program has to heat the air a little more in order to cover the temperature drop resulting from the operation of the adiabatic humidifier itself. Because adiabatic water air has the property that it causes, it ensures the reduction of the recorded air temperature. However, we declare here that we want it to be 20 degrees. Consequently, the program will automatically overheat the air in the heater, heat the air, so that after passing through the adiabatic humidifier, the temperature remained at 20 degrees. Under normal conditions, if we didn't do this, meaning it was 20 degrees on the inflow to the adiabatic humidifier, this adiabatic humidifier during operation would have caused a drop in the supply temperature by a few degrees, let's say 16, which would not meet our criterion of reaching the temperature behind the heater. Therefore, the program, it knows and calculates that it must heat the air to, say, 25 degrees in the first stage, so that after passing through the adiabatic humidifier and considering the temperature drop associated with the adiabatic process, the temperature behind it is 20 degrees and 40% humidity. Alright, let's calculate. And we see that we managed to reduce operating costs even further. So by introducing an adiabatic humidifier, we have 53,000. What can be said? That we reduced operating costs by 66%, which is a fantastic result. Not to mention the carbon dioxide emissions, as well as the amount of tons of oil equivalent. So if someone is developing white certificates, they can also use these calculations and observe in real time how many tons of oil equivalent they can save by modernizing the ventilation system. Well, and that's generally everything I wanted to show. I might also mention that, of course, we have the possibility performing calculations for VAV systems. In this case, additional fields are displayed where we can individually declare the supply and exhaust airflow for each hour of the ventilation unit's operation. Not only, because we declare it globally. That is one thing. Another thing, what will be the next stage in the development of this program is to introduce the capability for observation, what happens behind the individual sections of the ventilation unit, which is extremely, I think, also important, helpful. Then icons such as a thermometer will appear or be available. If we click on it, we will be able to observe how the air parameters behave behind the specific section of the ventilation unit. So here we have the air parameters at the air intake. Further, after passing through such a heat recovery exchanger, we already see the gray is the background representing the parameters of the intake air, the external row 1, and here we have what has been recovered, and in this case how the parameters change after the heat recovery section. We can zoom in on that. We can zoom out. This applies to every element. Okay, next we can observe what happens behind the fan, I mean behind the mixing chamber, sorry. Here we can already see how the mixing chamber also considers all these parameters behind the fan. So here we will definitely observe the general heating of the air behind the fan, and therefore a slight drop in relative humidity because the absolute moisture value is the same as with the heater. Well, here by choosing exactly what I said, the adiabatic cooler, so the program automatically preheats the supplied air in order for it to be behind the adiabatic humidifier. And to achieve 20 on the supply, because we had set 20 here, but the program automatically superheats, calculates the superheating of this air above 20 degrees, so that after here with the humidifier to achieve appropriate parameters, cooler. Here we had the cooling curve set, so here we also see how it takes shape, how the absolute moisture content changes. We also here, okay, and the humidifier, adiabatic. Here the temperature is also higher because I forgot to add that we also calculate it according to the heating curve, which means we implement thermoventilation. Therefore, we must also obviously have this higher temperature. Okay, and in this way we have reached the end of this presentation. So thank you very much for your attention. I invite you to explore this tool as I believe that in today's times and realities it is an extremely important element for which many investors will also be able to additionally add to the project because please note what savings this involves. We can easily prove to the investor that even he, by paying us some additional money for more precise here analysis of the topic, and not just a template approach where we select some ventilation system and it works for the next 20 years, generating some bills. It can really generate much lower bills and paying the designer for this type of analysis. This is really a fraction of what such a ventilation unit can generate. Thank you very much for your attention. I invite you to the next episode. Goodbye. Bye.